So fire that back up.
Yep.
So if you look at that Na2SO4Na, the only thing you really need to focus on is actually the SO42 minus, because the sodium isn't going to make any difference, because your sulfate has a charge of 2 minus. So if you look on this one, so you've got 4 oxygens, each with a charge of -2, so that whole thing has a charge of -8. So therefore sulfur has to be 6 plus. Now if you carried it all the way through the sodium, your alkali metals never change. They're always 1 plus. Your rare earth metals are always going to be 2 plus, okay? So those never change. So those are also kind of your anchors, right? So you got 6 plus. Now, this next one is one that you are going to use a lot, okay? This potassium permanganate, we're going to use potassium permanganate a lot. So I want to make sure everybody's cool with this. So basically, the only thing you have to focus on is that permanganate ion, which has a charge of 1 minus. So you got 4 oxygens, it's a -2, that gets you to -8. So the manganese has a charge of
7 plus.
plus 7, okay? You are going to use this a lot, okay? We're going to use permanganate ions a lot in this unit, so get used to it. So that's going to be plus 7. Now, here's the anomaly when we talk about these. If you look, sulfur actually is in the same column as oxygen. So you would think that they would have the same oxidation state. So when we talk about oxidation states, we're really not saying that the sulfur has lost 60 electrons. When you do redox reactions, this is more of a bookkeeping situation, because sulfur is not going to lose all 6 of its electrons. Okay, when you talk about like sodium, sodium is 1 plus. That is physically going to lose an electron. If oxygen is 2 minus, that is physically going to gain 2 electrons. But when you get into, especially like carbon, sulfur, and some of the weirder ones, it's a bookkeeping situation, but we're not saying like sulfur has lost 6 electrons, okay? Or manganese has necessarily lost 7 electrons, okay? But it is a bookkeeping way that works in this whole idea of redox reaction. Okay, now the N in NO3. Again, what's the overall charge of a nitrate anion? 1 minus, okay? I don't care what the calcium is, I can care less. Although I know it's 2 plus because there's a 2 out there. So you've got 3 oxygens, each of those at
2 minus.
-2, so that's going to be
6 minus.
-6, so nitrogen has to be
5 plus.
5
plus 5. Okay, you see the pattern for me?
Mm-hmm.
Okay, so then the carbonate, CO3 2 minus, right?
Mm-hmm.
So you got -6, carbon then is
4
plus 4.
Mm-hmm.
Okay, now here's what's different on NO2. So you can have NO2, which is nitrogen dioxide, or you can have NO2 1 minus, which is nitrate. Okay, there's a huge difference between the two. This is a gas, this is a soluble ion. Okay, they're completely different based upon the structure. So if it's NO2, which is what this is, everything adds up to 0. So if everything adds up to 0, what's the charge, what's the oxidation state of the nitrogen? Plus 4. Now, if it's nitrite, NO2 1 minus, oxygen is still -4, but in that situation, the nitrogen would be 3 plus. Okay? So that's why you have to keep track of, is it NO2, nitrogen dioxide, or is it NO2 with the charge of 1 minus, which is a polyatomic anion. 2 completely different substances based upon the oxidation state of nitrogen. Okay, so on F, what'd you get?
6 plus.
6 plus. What'd you get on G?
6 plus.
6 plus. H?
2 minus.
Minus 2.
2 plus.
2 plus and
4 plus.
4 plus. Beautiful. So we got those done. Now let's talk about number 2 on the element reduce. So you've got magnesium and copper nitrate, and this is like the lab that you're all going to do tomorrow. Is going to get you MgNO3 2, And again, this is like the Chem 1 version of this reaction because we still have the spectator ions in there. So basically, what's going to happen is this. You're going to take a chunk of magnesium, you're going to drop it into a solution of copper nitrate. The magnesium is going to dissolve, and the copper is going to begin to form elemental copper. Okay? That's what's physically going to happen. So, this is a single displacement reaction, okay? You've learned all this in Chem 1. You might have drawn a cute little poster for it, okay? Oh, you know, whatever.
My
Okay?
culture captain.
Ask me if I ever make my Chem 1 students, when I have taught it, draw posters. Ask me, I dare you.
Have you?
No.
Yeah, did you?
Okay. So, here's what's going to happen. Magnesium is 0, copper is 0, copper is 2 plus, magnesium is 2 plus. So which element is reduced?
Magnesium. Oxide.
Copper.
Copper. Copper is
Yeah.
reduced, why?
Because it lost electrons.
It went from 2 plus to 0, so it gained 2 electrons. So then the magnesium went from 0 to 2 plus, so it lost electrons. So the copper is the element that's reduced, the magnesium is the element that's oxidized. Now, in terms of the reducing agent contains what is oxidized. So the reducing agent is magnesium. Now, the oxidizing agent technically is going to be copper nitrate. You're going to list that whole thing, and here's the reason why. Because I can't go into the storeroom and just grab a bottle of copper ions, okay? I can't grab a bottle of nitrate ions. So my reducing agent or my oxidizing agent contains that whole thing that's being reduced or oxidized, okay? So this is why, if you look in this chemical storeroom, we keep all of the nitrates. When you walk in the chemical storeroom, all the nitrates are off on your right side. Those are kept completely separate because things that contain nitrates tend to be oxidizing agents because of the fact that they're going to be bonded with elements that have lost electrons. So we keep the oxidizing agents in one side of the room, we keep the reducing agents on the other because we don't want them to get together inadvertently because then you start chemical reactions. Okay? So that's why we keep them separately. So if you walk in, if you're looking for a nitrate, it's going to be over here on your right side. Strontium nitrate, magnesium nitrate, whatever that is. So because those contain elements that are going to be reduced, those oxidizing agents are over there. Okay. So on... I'll just give you this right quick. On B, the elements reduced is 10. Iron is oxidized. The reducing agent is iron. The oxidizing agent is tin chloride. And then on C, sulfur is reduced. The sodium is oxidized. The reducing agent is sodium. The oxidizing agent is sulfur. So then on number 3, is the reaction, the redox reaction. So A, B, and F are all redox reactions. The other ones are not. So again, just because you have a chemical reaction doesn't mean that it's a redox reaction. So if you look on C, you have a double displacement reaction, but nothing ever changed oxidation states. Yes, you're going to get, like on C, you would get a precipitate of silver chloride. Okay, but that doesn't mean that it's a redox reaction because the silver is still 1 plus and the chlorine is still 1 minus. So just because you have a reaction doesn't mean that it's a redox reaction. But if it's a redox reaction, it has to be a chemical reaction, if that makes sense. So anyway, we've kind of talked about everything that's there on, we talked about all those answers on the backside. Why can't a reduction without an oxidation? Because if something's going to lose electrons, something has to gain it. A single displacement reaction will always be a redox reaction because you're changing something from an elemental state of 0 into a loss or gain of an electrons. And then 6 is false because you can have a chemical reaction without it being a redox reaction. Okay, so stop that. I got something else to hand out next.